Let's now look at why the alternating series test is true and use that to understand how we can make an estimate on error terms in the alternating series test. Okay, so I'm calling this a proof between quotation marks. It's all the ideas of a proof. It's just not a complete proof. So the key idea behind the alternating series test is to consider the even and the odd partial sums. So just to make this concrete, I'm going to look at the alternating harmonic series, which we know converges by the alternating series test. And what we're going to do is we're going to look at even sums and odd sums. Okay, so let's start with the odd sums. So we can add up one term in the series. That's just S1. Then S3, we're going to take 1 plus that junk. Well, here we started with 1, and now we have negative a half plus a third. Well, that works out to being something negative, because minus a half is, a half is larger than a third, right? So because these terms are decreasing in absolute value, this guy is going to be more negative than this guy is positive, right? So that thing is going to be less than 0. And then that's going to be S3, so we get it by taking S1 and we add something negative. So S1 is going to be bigger than S3. Then if I take the next two terms, again I get something negative. So S5 is going to be smaller than S3. And if I keep going like this, right, each time I add up an odd number of terms, I'm going to get a smaller and smaller partial sum for my series. We have S1 is bigger than S3, is bigger than S5, is bigger than S7, is bigger than S9, etc. But on the other hand, if I do even sums, right here I have 1 minus a half, that's S2, and then here I have plus a third minus a quarter, so that's bigger than 0. And then a fifth minus a sixth, that's bigger than 0. So over here, I have that S2 is going to be smaller than S4, is going to be smaller than S6, and these are going to be increasing. And at each stage, to go from an odd to the next even, I go down, right? So that means that all the odds are going to be bigger than all of the evens. So we have this kind of behavior of the sequence of partial sums, that they're wobbling back and forth. And we have that the odd ones are a bounded monotone sequence. The even ones are a bounded monotone sequence. These are decreasing, and the even ones are increasing. So by this bounded monotonic sequence theorem, the even sums converge and the odd sums converge. And the key fact is that we assumed that the terms in our sequence here of these, in our series, that those terms are going to 0. That means that these partial sums have to have the same limit. Right, so that's sort of a sketch of the proof of this alternating series test. But this can give us some mileage now. Right? We can use this understanding in order to get the following result. What we get is that if we have an alternating series that satisfies all the hypotheses of the alternating series test, so in other words, we have an alternating series, the terms are decreasing after we take their absolute values, and the limit of the general term is 0, then if I approximate my series by a partial sum, the error I get is going to be smaller than the first term that I've forgotten about. So this is how we can use the alternating series test to make approximations of our series. Okay, let's do a quick example of what that looks like in practice. So this is a problem I've taken from the book. So here we're given this series, sum k equals 1 to infinity, minus 1 to the k plus 1 over k. This is the alternating harmonic series. The book tells us that the limit of this thing is the natural log of 2. It's not important to know that, but it's kind of a fun fact, and we will see this again in the material from Chapter 11. So this is a little foretaste of Chapter 11 material. But really here, all we're doing is we're looking at this alternating harmonic series, and we want to understand how to get an error term that's small. Okay, so we just go ahead and check, right? So we check the hypotheses of the alternating series test. We did that already, so I'm going to just give us a check mark, right? So in principle, we need to check it's an alternating series, which it is. We need to check that that 1 over k is a decreasing sequence in k. It is. And we need the limit of 1 over k to be equal to 0. Right? Those are the three things we need to check to use the alternating series test. It checks out. So then the next thing to do is we need to remember what our formula gave. And so that says that the value of our series compared to a partial sum to some number capital N this is less than or equal to the absolute value of this term at n plus 1. So is smaller than the absolute value of the first term we've left off. So that's going to be 1 over big N plus 1. We want this to be less than 10 to the negative 4. So we can go ahead and solve that. We want n plus 1. We want that bigger than 10 to the 4th, right? I'm taking the reciprocal of that inequality, and when you take a reciprocal with positive numbers here, it flips the sign. And so that gives us that we can take n to be greater than or equal to 10 to the 4. So let's say n equals 10 to the 4. Right, so that's what we need, and it says how many terms must be summed. So normally people mean what's the smallest number we can take. So 10 to the 4th does the job.